In this video, I'm trying to solve some question for chapter 5. So in this question, we have a nozzle that water goes through it and exists at a free jet. Now in part A, we are trying to find the anchoring force that can hold the elbow. Now, first when we say anchoring force, the first way that we can solve to find anchoring force that comes to our mind is conservation of momentum because because we can apply the forces there, right? So there are some steps that I told you in the previous video to follow them to solve the question in this chapter, right? So the first step was to define your appropriate control volume. And if I want to define my control volume, let me just, so I'm starting from the opening right here, and then coming here, and then I know the pressure right here. Sorry, I know the pressure right here, and then this is my control volume. The next step was to assign our coordinate system, right? So this is the coordinate system that we have. And the other step is to define the velocities going in to the system and then the kind of the inflow and outflow, right? So this is the velocities going in and this is the velocities coming out of the system. And let's call this section 1 and then this section 2. So we can say that this is V1 and then here we have V2, right? And then after that, we need to show the forces here, right? And we know that in linear momentum, there are some type of forces that we have. The first one is the forces that happen due to the pressure at the openings. The second one was the weight of the control volume, and then the last one was the reaction forces, which is like the anchoring force. So let's assume the anchoring force is going to be in the positive direction of x and y, right? And then we're gonna have weight, right? And then the other forces that I mentioned is the pressure at the opening, right? So this is going to be P1 and then this is going to be P2, right? So now I show all of the forces. Now let's get started with to apply. Um, First, let's just write down the assumptions that we have in this question. So the assumptions that we can make is first to consider this flow as a steady state, and we have water, so we can say this is incompressible flow. And this is also 1D, and then we have constant properties, right? So now if I apply the conservation of mass, so we can simply say that the one flow is coming out and is going to the system and coming out of the system because we have just two openings. So we can easily write down m dot 1 is equal to m dot 2 equal to our flow rate, right? And we know that the formula for flow rate is rho VA. So if we just write it down for the two sections that we know that we have and the same fluid, so we have the same density, and then, oh sorry, these are two. Okay, and then now we know V1 and we know A1 because we know the diameter of one, and we know A2 because we know the diameter of two. So let's solve it for V2. Now V2 is going to be V1 times A1 per A2, and then from here A1 is also because the cross section is the circle, right? So, and this is the formula for area of a circle, right? And then from here these are going to be cancelled out. Now V1 is 1.5 meter per second, and D1 is 0.3 meter, and we need to square it, and D2 is 170 millimeters, and we need to convert it to meter, right? And this is how we convert it to meter. So we write the diameter at section 2 as well. So from here we're gonna get V2 is equal to 6 meter per second, right? So this is the V2 that we have, and let's also calculate m dot, the mass flow rate, because we know that in momentum equation we need mass flow rate. So let's just calculate it. So m dot is going to be rho 1 v1 a1, and if we just put all of the value here, we're gonna get 106 kilogram per second. So this is the value for m dot as well. Now let's apply the conservation of linear momentum from 1 to 2, right? So this is the formula that we have for conservation of momentum, and this is the simplify that of the original equation because of the assumption that we made here, right? So we don't have the term of that has d over dt because it's a steady state, and sorry, and this is what we have for the linear momentum, and we know that this term is m dot, and the sign is depends on if it's inflow or outflow, right? And then this v, the sign of the velocity, it depends on the direction based of the coordinate system that we consider. Now let's just apply it. If I use it, and first let's just use it in x direction, right? In x direction, I have fx right here and also here. And then I also have, what else I have? I have P1 right here and I have P2 right here, right? So these are the three forces in x direction that I have. So let's just write them down, and we need to multiply P, which is pressure, by the area to get the force. And then also I have P2A2, which is equal to, let's just use the right hand side terms. So I have V1, right? And the direction, it's in the positive of the x direction if you look at it, so it's positive. And then we have m dot, and the m dot is in flow right here, right, at section 1. So we have a minus sign here. And then we have V2, which if we look at the V2, it's going this way, so this is negative, and it's outflow, so we have a positive mass flow rate. And if we just factorize m dot, we're gonna have m dot times V1 plus V2, right? And if I put all of the value here, I'm not going to write down all of the value because you have everything here. So you have P1 here, and then you have the area we just calculated. We have V2, we have m dot. So if we put all of the value here, and just don't forget to convert the P1 because it's kilopascal and we want Pascal here, right? So let me just write down for, to see how I multiply this one by 1,000 to change the unit of kilopascal to Pascal. And we know that Pascal is Newton per meter squared. And this is my area that I have, and minus the mass flow rate with both velocity that I have. So from here we get the Fx as minus, we get it Fx as minus 857 Newton, and this is negative, so it means that the direction that we assume for Fx is wrong, and Fx is going to this direction. And now we find Fx, so let's also apply the conservation of mass in y direction. In y direction, let's see what we have. So the forces that we have is this Fy here, is this weight here. Let's see if we have also velocity in this direction. So we don't, we just have velocity in y direction. So now let's just write down the formula. So we have Fy, which is positive, we have weight, which is negative, and then we don't have any velocity in the y direction, so it's going to be 0, the second term, right? This term is going to be 0. Now from here, Fy is going to be equal to the weight, and we know that weight is gamma of water times the volume, and the volume we have it in also in the question. Now let's just put all the values that we have. So we have 9.8 times 10 to the 3 Newton per meter cubic, and then this is the volume that is given through the question. Now from here, Fy is going to be 1417 Newton, right? So this is the Fy that we get. But in the question, it said that they wanted us to find the magnitude of F. And by physics, we know that the magnitude of F is going to be the square root of the force in x direction squared plus the force in y direction squared, and then from here we get 8695 Newton. And if we want the direction and the theta between Fx and Fy, we just say that Fx is wrong, the direction that we guess was wrong, so this is Fx right now. And but the Fy that we got was positive here, so we have Fy here. And if I say this is my total F, so this is theta, and let's just show that this is also my theta prime. So let's see how can I get theta. So we know that theta right now, if we look at the this shape and solve it through the math, we can get that tangent inverse of minus fy over fx is going to be minus 9, 7, right? And then if we just look at the theta prime is 180 degree minus this degree that we got here. So it's going to be 170.3 degree, right? And this is the direction if they wanted us. Now let's go to the part B. They wanted us to find the loss of the elbow, right? The energy lost from the elbow, actually. So part B, now we are trying to find the loss, and we know that the loss is in conservation of energy. And we are going to apply it from 1 to 2, right? So if I write down the conservation of energy, I know this is P2. I'm writing it from 1 to 2, right? So over gamma plus V22 over 2G is like Bernoulli equation, but they have the shaft work and head loss as well. So plus Z2 equal to P1 gamma plus V1 squared over 2G plus V1 and plus the shaft work head and minus the HL, which is the head loss. And they wanted us to find loss, and we know loss is kind of HL times G, right? Now if we find HL and then multiple HL by G, then we can get loss. So this is why we need to find HL. Now let's see what values, what variables I have and which one I don't. So P2 is right here. We should know that it's to the atmosphere, so it's going to be 0 here. P1, we know P1, and then there is no work here. There is no turbine or pump or any other work here, so it's going to be 0. And then if we look at the elbow, we just kind of neglect, we can just say that the change in potential energy is, we can just neglect it because it's this elevation right here is not that much, so we can just say that Z1 is equal to Z2, right? So then these two gonna cancel out as well, right? And then yeah, let's solve it for HL. So if I just rearrange it, HL is going to be P1 over gamma plus V1 squared minus V2 squared over 2G, and we want loss. So let's multiply this HL by G, and then if we do that, we're gonna get P1 over rho. It's going to be rho because this is rho G, and if we multiply it by G, G cancel out, so we're gonna have rho in denominator, and then plus V1 squared minus V2 squared, and the G is gone because of we multiply it by G, right? So this is what we have for loss, and if we put all of the value there and remember to convert kilopascal to pascal, so we're gonna get loss value as 93.23 meter squared per second squared, and so this is the loss that we got. And let's see what they wanted us for part C. They wanted us to find the energy, the energy loss again, but this time from the nozzle exist to the where the water comes to the rest. So if we just assume that the water is coming out of, not assume that the water is coming out of the nozzle from here, and just let's say that at point 3 here, it's going to go to the rest, right? Now and we want to find the loss from 2 to 3, right? So this time, let's just write down this is part C. We try to find the loss, and then let's use again the conservation of energy, but this time from point 2 to 3. So if I write down the formula, I'm going to have P3 over gamma plus V3 squared over 2G Z3 equal to P2 gamma V2 squared over 2G Z1 plus HS minus HL, right? And now if we look at the pressure at P2 and P3, both are in the atmosphere, so both the value is going to be 0, and 2 to 3 they are in the same elevation, so Z1 and Z3 and oh, this is Z2, I write it down wrong. They are going to be cancelled out, right? And then we said that here the flow, oops, here the flow is coming to the rest, right? Means that V3 is going to be 0. So V3 is going to be 0 also. And we also said that we don't have any kind of work here. Now, if we just rearrange it to solve it for HL, we're gonna get HL is equal to V2 squared over 2G, and if we just multiply both side by G, we're gonna get loss, right? And then from here, loss is going to be 18 meter squared per second squared. So now I'm going to solve the next question on the next video.